New idea, permutation. Suppose S is a set of n elements. A permutation of S is a non-repetitive list of length n made from all the elements of S. For example, let's say S is this set. One possible permutation of S is the list A, B, C, which, by the way, we can also write as the string ABC. String is just a shorthand for representing a list. Another permutation of S is the list B, A, C, which can also be written as the string BAC. Right, so the point is a permutation is a non-repetitive list of length n, meaning n is the number of elements in the set. So the permutation also has n entries, and it includes all the elements of S in the list. However, the list A, B is not a permutation of S because it does not include all the elements of S, and the length of this list is not 3. Similarly, this list A, B, C is also not a permutation of S because it's repetitive, and also the length is not the same as the number of elements in the set. Okay, so now we can ask a question. If we have the set ABC, how many permutations does this set have, right? How many possible permutations can we make? So one approach is to list all the permutations of the set and count them. So the permutations of the set are, all the possible permutations are ABC, ACB, BAC, BCA, CAB, and CBA. So if we count them, we see there are 6 permutations. So that's one approach. Another approach is to use the multiplication principle, meaning we don't actually have to list out all the possible permutations in order to count them. So here's the idea. To create a non-repetitive list of length 3 using the elements of the set, right, which is what we need to do in order to make a permutation, we have the following. We have 3 choices for the first entry, right? Because again, we're making a list of length 3 using the letters A, B, C. So for the first entry, we have 3 choices. For the second entry, we only have 2 choices because it's a non-repetitive list. And finally, for the last entry, we have 1 choice. Thus, by the multiplication principle, there are 6 permutations of this set because well, it's the multiplication principle. There's a certain, there's a certain number of choices for each entry, and multiplying them together tells us how many different possible lists we can make, right? So the multiplication principle tells us, given these number of choices for each entry, how many possible lists can we make? In other words, in this example, how many permutations can we make? So that's 6 for this example. How about this? How many permutations does the empty set have? Okay, now we have to make sure we have our definition straight. So recall the definition. Again, a permutation of S is a non-repetitive list of length n. So in this case, n would be 0 because that's the cardinality of the empty set. The empty set has 0 elements. So we need to make a non-repetitive list of length n made from all the elements of S. Well, now this set S has no elements, so we need to make a list. If possible, we need to make a list that's non-repetitive of length 0 made from no elements. And in fact, there is such a list. The only non-repetitive list of length 0 made from all the symbols of the empty set is the empty list. So the empty set has exactly 1 permutation. Now we have this related idea of factorials. If n is a non-negative integer, then we say that n factorial, which we denote like this, is the number of permutations that can be made using a set of n elements. So for example, based on the previous examples, we know that 3 factorial is 6. Since the 3-element set ABC has 6 permutations, as we saw. So 3 factorial, meaning the number of permutations that can be made from a set of 3 elements is 6. How about 0 factorial? You might say it should be 0. However, we saw from the previous example that it's really 1, since the 0 element set, right, the empty set, has 1 permutation. So 0 factorial is 1. Now we want to come up with a general formula for n factorial. So if I give you any positive integer n, can you tell me what n factorial will be? All right, what about 15 factorial, for example? So here we use the multiplication principle in our reasoning. So to create a permutation of an n element set, where n is any positive integer, right? N is greater than 0, it's a positive integer. I didn't say here, I didn't write the word integer, but it's implied, or not implied. I'm telling you it's an integer. So to create a permutation of a set of n elements, how many choices do we have for each entry? So we have n choices for the first entry, because we can use any of the n elements of the set as the first entry. But now for the second entry, we have only n minus 1 choices, because a permutation does not allow repetition. So there are n minus 1 choices for the second entry. There are n minus 2 choices for the third entry, and so on. Finally, there are 2 choices for the next to last entry, and there's only 1 choice left for the last entry. Thus, by the multiplication principle, we can see that for an integer n greater than 0, n factorial is equal to n times n minus 1 times n minus 2 dot 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 times 2 times 1. For example, what is 6 factorial? 6 factorial is, according to this formula, 6 times 5 times 4 times 3 times 2 times 1, or 720. Here's an example where we use factorial. Consider a list of length 7 made from these 7 letters. Question A, part A, how many such lists are there if repetition is not allowed? So if we're trying to make lists, how many can we make if we do not allow repetition? Well, this is just, there are 7 letters, so the number of lists is 7 factorial, or 5040. There are 7 letters, no repetition, so 7 times, the number of choices are 7 times 6 times 5, and so on. In other words, 7 factorial. Part B, how many such lists are there if repetition is not allowed, and the first 2 entries must be vowels? The first 2 entries must be vowels, and again, repetition is not allowed. So there are only 2 vowels among the letters, right? Among these 7 letters, there are 2 vowels, and the rest are consonants, meaning not vowels. Thus, in a list, right, we're trying to create lists here. So in every list, the first 2 entries must be vowels, and the final 5 entries must be consonants. By the multiplication principle, the number of such lists is 2 times 1, because those are for the first 2 entries, which have to be vowels. And then we have 5 letters left. So we have 5 choices, and then 4, and so on. So this gives us 2 factorial times 5 factorial possible lists, or 2 times 120, or 240 such lists. Another example, again, consider lists of length 7. The same setup, but now part C. How many such lists are there in which repetition is allowed? Okay, so now we are allowing repetition, and the list must contain at least 1 repeated letter. So not only is repetition allowed, but the list has to contain at least 1 repeated letter. At least 1 of the letters in the list has to be repeated. Okay, so how many such lists are there like that? So here we're going to use the subtraction principle. So let U be the set of all lists made from these 7 letters with repetition allowed. What is the cardinality of U? Well, we know it's 7 times 7 times 7, or 7 to the power of 7, because repetition is allowed. So each entry has you have 7 choices for each entry. Okay. Now we want to find the number of lists that have at least one repeated letter. So we will subtract away from U all those lists that have no repetition. Okay, so again, we're trying to find out how many lists have at least one repeated letter. Now that's a little difficult to count. So instead of counting that, we're going to start with the universe, and we're going to subtract away from U all those lists that have no repetition. Right, that's the ones that we're not interested in, so we're going to remove those. Okay, so let X, which is a subset of U, be the set of the lists in U that have no repetition. Right, so this is a subset of U, but this is all those lists that have no repetition, and that's what we want to remove. What's the cardinality of X? So again, we're talking about a lists of length 7 that have no repetition. So that's 7 factorial, or 5040. By the subtraction principle, okay, this is a typo. This S should not be there. By the subtraction principle, another typo, the number of lists that have at least one repeated letter, okay, the number of lists that have at least one repeated letter. So in other words, the universe, the cardinality of the universe minus minus X. Again, the cardinality of the universe minus X. In other words, everything in the universe except for those that have no repetition is the cardinality of U minus the cardinality of X. That's the subtraction principle, which gives us this result. K-permutations. So similar idea as a standard permutation. Let S be a set of n elements, and let K, which is less than or equal to n, be an integer. Okay, so we have n elements in a set, and then we have another number, K, which is less than or equal to n, which is and K is an integer. A K-permutation of S is a non-repetitive list of length K made from K elements of S. Okay, so standard permutation is where we use all the elements of S. A K-permutation is where we use K elements of S, and we make a non-repetitive list of length K using those K elements of S that we chose. So we have this notation: the number of K-permutations of an n element set is denoted like this: permutations and P n comma K. Okay, permutations of an n element set, K-permutations. The K-permutations of an n element set. How many do we have? And that's denoted like this. So let's say we have this set. Okay, so how about a 0 permutation of S? So there is one, and it's the empty list. Thus, P 3 comma 0 is 1, is equal to 1. And the number of permutations, the number of 0 permutations of a 3-element set is 1. How about this? How about 1 permutations of S? So here we're looking for lists of length 1 made from 1 element of S. So we have only 3. A, that's 1. B, that's a second. And C. So those are the 3 1 permutations. Thus, P of 3 comma 1 is 3. The 6 2 permutations of S are these. Thus, this. There are 6 3 permutations of S. So again, a 3 permutation would be a permutation of 3 of the elements of S, which happens to be just the same thing as the permutations of S, because S has only 3 elements. So those are ABC and so on, ACB, BAC, BCA, CAB, CBA. Thus, P of 3 comma 3 is 6. How about 4 permutations of S? How about 4 permutations of S? So there are no 4 permutations of S, as such a thing would be a non-repetitive list of length 4 made using only 3 objects, which is impossible, right? What would a 4 permutation of S look like? You would have to have a list of length 4 non-repetitive list made using these, made from these symbols, but there are only 3 symbols there, so not possible. Okay. Thus, P of 3, 4 is 0. Now we want to find a general formula for Pn, k. So we have the same reasoning as before. To create a k-permutation of an n-element set, well, not the same reasoning, the same type of reasoning, sorry, same type of reasoning as before. So we think about it like this. If I want to make a k-permutation of an n-element set, where n is greater than 0, we have n choices for the first entry, right? Because we could choose any of the n elements of the set as the first entry. We have n-1 choice for the second entry, n-2 choices for the third entry, and so on. Now, as we go on, how about for the ith entry, right? How about for entry number I, where I is some entry in the middle, right? How many choices do I have? Well, if you notice the pattern here, it's n-2 choices for the third entry. It's n-1 choices for the second entry. So the general pattern here is that it's n-I plus 1 choices for the ith entry. Okay, so like so this here we're talking about for the third entry, so that would be n-3 plus 1, which is n-2 choices for the third entry. So the general a general entry number I, where I is some entry in the middle, you can have n-I plus 1 choices for that entry, and so on and so on. And finally, when you get to the kth entry, so for the kth entry, how many is it going to be? Well, following the same pattern, it's going to be n-k plus 1 choices for the kth entry. Thus, by the multiplication principle, we see that for n that's greater, for any n greater than 0, P of n, k. Well, I should have added here that, you know, k has to be less than or equal to n, but okay. So again, assuming that k is less than or equal to n and n is greater than 0, then P of n, k is equal to n times n-1 times n-2 ... times n-k plus 1. Note, what are we doing here in this formula? We are multiplying k numbers, right? Because we're trying to fill up k entries. So we have to multiply k numbers to find the result, since there are k entries to fill. Okay, so here's the formula. Now let's use it in some examples. So what is P of 10, 11? That would be 10 times 9 times 8. So we have to multiply 11 numbers together, right? So it's going to be 10 times, and each time we go down by 1, right? Each number we go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 0. So these are our 11 numbers. When you multiply them together, guess what? You get 0, which actually makes sense, because this would be saying how many 11 permutations are there of a set of 10 elements, right? Well, if there are only 10 elements in the set, it's not possible to make an 11 permutation. It's not possible to make a permutation of length 11. So that's why the answer is 0. How about P 10, 10? So that's 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. Okay. How about P of 10, 9? And P of 10, 8, and so on. P of 10, 4, P of 10, 3, P of 10, 2, and finally P of 10, 1. That's just 10. There's nothing, you just put down the 10, there's nothing to multiply it with. So here's an example. 10 contestants run a marathon, all finish. So all the contestants finish and there are no ties, so you don't have to worry about that. Question, how many different possible rankings are there for first, second, and third place? Okay, so we have 10 different people. There's going to be one first place, one second place, one third place. How many possible rankings are there among those 10 people, right? Each person could either be first, second, or third, but not everyone is going to be first, second, or third. So how many different possible rankings are there? So let us call the contestants the letters A through J. A ranking of winners can be regarded as a 3 permutation of the set of 10 contestants, because what are we doing when we're ranking winners? We're taking three of the 10 contestants and putting them in some order. So that's a 3 permutation of the set of 10 contestants. For example, ECH would mean that E is in first place. So ECH is a permutation, right? It's a 3 permutation of the set of these contestants. And it means that E is in first place, C is in second place, and H is in third place. All right, so a ranking of winners can be thought of as a 3 permutation of this set of 10 players. Thus, there are P of 10, 3, which is equal to 720 possible rankings. Now, you didn't really have to use this notation in this question, right? You could have just used the plain multiplication principle to figure it out without even thinking about this notation, permutation, P 10, 3 notation. However, it is a nice little shorthand. Okay, for the next example, we have to talk about what a standard deck of cards looks like. So this is an image I grabbed from a table I grabbed from Wikipedia. So so we see that a standard deck of cards has all these cards. There are 52 cards in total, and the cards are broken down into 4 suits: clubs, diamonds, hearts, and spades. Okay, so those are the rows. There are 4 different suits. Each suit has 13 cards. And then each suit, each of those, those 13 cards are broken down into here are they. So there's ace, there's 2, 3, 4 through 10, then there's jack, queen, and king. Right, so for example, this card right here is a 9 of diamonds, right? So, okay, or this would be a queen of diamonds. This one would be an ace of spades, right? Okay, so that's the idea. Also notice that 2 of the suits are red, right? Diamonds and hearts. And 2 of the suits are black. Those are the clubs and the spades. Okay, so we'll have to keep that in mind. And then the only card is these cards here in the right 3 columns are known as face cards because they have pictures of people's face. They have pictures of faces on them, right? So the jacks, the queens, and the kings are known as face cards. Okay, so now let's look at an example. You deal 5 cards off of a standard deck and line them up in a row. Okay, so suppose we do that. I guess I should have added the word suppose there. Okay. Question: how many such lineups are there? Okay, again, random 5 cards. You take off the deck and you line them up in an order, in a row. Okay. How many different possible lineups are there? Well, there are 52 cards in the deck. The number of ways to line up 5 of them is P of 52, 5, because there are 52 cards. So we have a set of 52 things, and we want to take 5 of them and put them in some order, right? A permutation is an ordered list. It's a list. It has an order. So so this comes out to be, well, a very large number, over 300 million. Okay, next question. How many such lineups are there that either consist of all reds or all clubs? Okay, so again, we're taking 5 cards off a deck, and we want to know how many different ways are there how many different lineups are there where all 5 are red or all 5 are clubs. Now notice that if a card is red, then it is not a club. And if it is a club, then it is not red. Let's look back at the chart. Right, so all the clubs are black and all the reds are not clubs. So clubs and reds never mix. So we can divide the possible lineups into 2 non-overlapping categories. First category is that we have 5 red cards. Second category is we have 5 club cards. And again, we don't have to worry about overlap here, and that's very important for this example. We don't have to worry about overlap because if a card is red, it's not a club, and if it's a club, it's not red. So these are totally distinct, non-overlapping categories. Okay, now there are 26 red cards. So how many ways are there to make a lineup of 5 red cards? There are 26 red cards in total. So the number of ways to line up 5 of those 26 cards is going to be P of 26, 5, or this number. How about for the second category? Well, for the second category, we have 13 clubs. And the number of ways to line up 5 of them is going to be P of 13, 5, or this number. Now we can use the addition principle. We have these 2 categories. They are non-overlapping. So in other words, we divided up all possible lineups that we're interested in into 2 non-overlapping categories. So now we just need to add them up. All right, so we add up P of 26, 5 with P of 13, 5, and that gives us this answer, about 8 million. About 8 million. Okay.